Hi, my name is Nir Levine, and I'm a third year at UC Berkeley, majoring in EECS. At Underwater Robotics at Berkeley, I'm now the president, previously the project manager of the perception team. I worked on background thresholding as well as streamlining our code base structure for computer vision to make testing our algorithms easier.
Hi, my name is Karthik Thamarajan, and I'm a rising sophomore at UC Berkeley, majoring in electrical engineering and computer science. At Underwater Robotics at Berkeley, I'm the perception product manager. I worked on the general background removal algorithm that we are using on our sub.
Hi, I'm Ashwin, and I just finished my third year at UC Berkeley studying electrical engineering and computer science. At Underwater Robotics at Berkeley, I'm the controls lead.
So in general, our algorithms for identifying objects of interest, such as the gate with two posts, in the input video feed from the sub involve thresholding out the background water. Usually, the threshold was based on color, for example, a certain shade of blue. This would isolate the object and simplify the process of identifying its location based on the contours of the thresholded image. This method, while somewhat effective for each task individually, wasn't very reliable and scalable since we would manually hardcode the color threshold for each task, and even separate points of time in each task, in a single task. In addition, thresholding by color often wasn't enough to get a stable contour of the object of interest, and thus noise was a glaring issue. So this method worked out at first, but we definitely wanted to come up with a better strategy.
In order to create accurate perception algorithms, the approach to find a specific task is to first run a general background removal algorithm, followed by a more specific algorithm. This approach can help focus the output of a specific task algorithm to salient areas within the image. The general background removal algorithm utilizes two separate background removal algorithms, which excel in different ways. There's an intelligent switching algorithm that changes which one of the two algorithms are used at any given time. One algorithm is an implementation of minimum barrier saliency object detection, shown by the two images on the left, which tend to produce results robust to noise. The other algorithm utilizes k-nearest neighbors to produce an efficient and full output of salient objects, shown by the middle images. The images on the right show the final output both in the form of a contour and in the form of an interpolated rectangle in order to bridge the gap between any switching that may occur in the middle of the running segment.
In order to test our control algorithms without access to physical testing, we utilized the open source UUV simulator in Gazebo and its ROS2 port called Plankton. We modified the base submarine models of the simulator to best match our own sub's mass, inertia, and sensor architecture. Using the simulator also gives us an additional advantage of comparing our algorithms against the simulator's ground truth. We were able to compare how our velocity and orientation PIDs performed when using the noisy IMU readings as sensor measurements compared to using the actual robot pose and twists as sensor measurements. This allowed us to know whether any fault or error in the algorithm was due to the algorithm implementation or due to the noisy sensors. In this video, we can see an example of running our velocity and orientation controller in parallel with it using the IMU sensor as the input to the PID controller. And we can see that the robot is able to smoothly and efficiently go from one location with orientation to another location in orientation.